Hello, this is Ed Chapman, and this video cast is going to cover the properties of water that arise from hydrogen bonding. Now, we're going to start with water. What exactly is water? Well, water is a molecule made up of two hydrogen atoms bonded to a single oxygen atom. So, this whole thing here, which kind of looks like an upside down Mickey Mouse, is a water molecule made up of three atoms, two hydrogens and one oxygen. Now, each of these hydrogens has a nucleus, represented here with these red spheres. And of course, there's only a single proton in each hydrogen. And the oxygen nucleus is massive by comparison. It's got a bunch of protons and neutrons here, and each is surrounded by electrons. Now, you make a molecule, one of the ways you can make a molecule is by forming what we call covalent bonds. Okay, now that means that this hydrogen atom is held to this oxygen atom by a bond. And this one over here, same thing, by a bond. And this bond is actually formed by a pair of electrons, represented here by these blue spheres. So each covalent bond is made up of a pair of shared electrons. Now, what makes it polar covalent, which is the important idea here, is the oxygen nucleus is able to attract this pair of electrons much more strongly than this hydrogen nucleus is able to. So that means this pair of electrons exists more closely on average to the oxygen's nucleus than to either of these hydrogen nuclei. So that means, because electrons carry a negative charge, that the oxygen atom, get rid of that, the oxygen atom picks up a net negative charge associated with this end of the molecule, the water molecule, and each hydrogen atom has an associated positive zone at its ends as far as you can get from this negative end. So that means that the water molecule kind of has a negative end and a positive end, and this gives it a polarity. And it's this polarity that produces what we call hydrogen bonds. Now, in liquid water, each water molecule, represented here by these little Mickey Mouses, are attracted to each other by what we call hydrogen bonds. And hydrogen bonds are formed between the negative oxygen end of one water molecule and the positive hydrogen end of another nearby water molecule. And so positive and negative attract, and we get what we're called hydrogen bonds. Now, hydrogen bonds are constantly forming and breaking and forming and breaking. They're not permanent. And hydrogen bonds form more, they become more stable the cooler the water is, until finally they crystallize when water turns to ice, and they become less stable or destabilized by heat as water warms up. So if you heat water hot enough, the hydrogen bonds all break and each water molecule goes flying off by itself, and the liquid turns into a gas. So here is a review of what we just talked about. Now, because water forms what we call hydrogen bonds, properties emerge from water that are very important in biology. And these are surface tension, capillary action, the moderation of climate, evaporative cooling, and the fact that ice doesn't sink, it floats on liquid water. Now, one of the ways you can think about hydrogen bonding between water molecules is cohesion. Cohesion is the attraction of like substances to like substances. So water is attracted to water. Water holds itself together. So if you've ever thrown a handful of water up into the air, you notice it immediately forms little droplets because each water molecule is attracting itself by way of hydrogen bonds to all the other nearby water molecules, pulling the whole liquid into the tightest shape you can get in 3 dimensions, which is a sphere. We have a word for this. It's called cohesion. Now, the cohesiveness of water produces something called surface tension. This is kind of cool, I think. If you look at a cross-section of liquid water, the water molecules that are below the surface are attracted in 3 dimensions to all the other nearby water molecules by hydrogen bonds. These black arrows represent hydrogen bonds. The water molecules at the surface, on the other hand, they are not attracted to air. So they are literally being pulled downward and to the sides by hydrogen bonds, but not upward. So that makes the surface of the water a little stronger, a little thicker, kind of like a skin. And this skin is stretched, it's under tension. It's a tension that holds together soap bubbles. You've seen lots and lots of manifestations of this in everyday life. This is important to many pond creatures like this water strider, because if you're able to distribute your weight enough, okay, if you notice this little guy has 4 legs that are actually pushing down on the water, plus these 2 in the front for a total of 6. This little pond skater is actually able to stand on the surface tension of the water because it's his little feet, the hairs on its feet, do not form hydrogen bonds. So he literally can't get wet. The bottoms of his feet can't get wet, so they push away on the water molecules and cause the surface to deform downward. So visually, you can see the skin or the surface tension of the water because of the weight of this little insect pushing down on it. Another emergent property of hydrogen bonding is what we call capillary action. And capillary action is actually made up of the combination of the cohesiveness of water molecules to each other plus the adhesiveness of water molecules to other substances. Water adheses to things that can get wet. You probably know that cotton material can get wet, paper absorbs water, soil, sand, things like that absorbs water because they're able to form hydrogen bonds with the water molecule. But because these materials are not water, we use the word adhesion. Cohesion, remember, is the attraction of water to itself, or water holding together in like a droplet. And adhesion is the attractiveness of water molecules to other substances. These two forces combine to produce something called capillary action. Now, we can look at capillary action in a very simple setup here. If you take a container of water and you put a glass tube in it, the water will actually move up into the glass tube against the force of gravity above the surface level of the water. So for example, in this glass tube, the water has moved up this far. And in this glass tube, you'll notice the water has moved up about twice as far. Now what's the difference? Well, it's the diameter. Scientists have figured out that water is able to move up thinner tubes farther than fatter tubes. So if you make the tube thin enough, the water can actually move a remarkable distance against the force of gravity without anything having to push it. Now, physics-wise, the weight of the atmosphere is actually what's causing the push here, but we're not going to worry about that in biology. That's more of a physics thing. So this is important to plants because plants use capillary action to suck water up into their tissues. And if you look at the tissues of plants in cross-section here, you can see that the plant tissue, or the wood, is actually made up of millions and millions of very, very fine tubes made of a material very similar to paper, cellulose. So what's going on here? Well, the water molecules are being attracted to each other. That's cohesion. And the water molecules are actually being attracted to the sidewalls, or the material of the tube. Over here it's a glass tube. Over here it's basically a paper tube. So the combination of the water sticking to the sides of the tube and the water molecules sticking to each other allows the water molecules to move in an upward direction. And this is how plants are able to translocate massive amounts of heavy water from the soil up through their tissues and into their leaves, where it's being evaporated constantly and it constantly needs to be replaced. Another emergent property of water, is specific heat. Now, specific heat is actually arising from the fact that water molecules are cohesing, or they're hydrogen bonding with each other. Let me show you what I mean. Specific heat is a property of all matter. Water happens to have a specific heat of 1.0. So what that means is it takes 1 calorie of energy to raise 1 gram of water 1 degree Celsius. Okay, so this is actually the definition of a calorie. A calorie is the amount of heat that it takes to increase the temperature 1 gram of water 1 degree Celsius. So this means what's going on when you heat water up is you are causing the water molecules to move around faster and faster. And the more the water molecules are moving, the less able they are to form hydrogen bonds. So eventually, if you add enough heat to the water molecules will no longer be able to hydrogen bond with each other, and they'll go flying off as individual molecules of water as a gas, no longer be a liquid. So water has a specific heat of 1.0, which means it takes a lot of energy to cause these hydrogen bonds to break. And compared to other materials, water has a very high specific heat. And this is important in biology for a number of reasons, and let me show you what I'm talking about. If we look at a climate map of the southeastern United States, we know that large bodies of water have a moderating effect on climate. So out here we have the Atlantic Ocean, okay, and if you just go by latitude, okay, which is the distance north or south, okay, you can see that the warmer areas kind of curl up on the coasts and the colder areas kind of dip down here in the interior. So if you lived right here in North Carolina in November, you would be experiencing a milder fall or a less cold fall than if you lived out here in Kentucky on average. And this is because the Atlantic Ocean water in November has absorbed a lot of heat over the summer, but that heat doesn't go away immediately. It has to be released slowly. So in the early part of winter or late fall, the Atlantic Ocean is giving up heat to keep the climate or keep the air here near the coast warmer in general compared to the air here over the interior or more inland areas. So this has a huge effect on the plants and animals that can live in different areas because, of course, climate is an important abiotic factor in ecosystems where different ecosystems are. Water also, because it has such a high specific heat, it takes a lot of heat to cause water to evaporate. The heat has to come from somewhere. So what if you're a kangaroo living in the outback of Australia and it's extremely hot, say 115 degrees Fahrenheit? This kangaroo can't sweat because sweating causes you to lose a lot of water. So rather than waste a lot of water trying to cool its whole body down, the kangaroo spreads saliva on its forearm. The saliva evaporates and cools its blood, which is being pumped through capillaries in its arm. So this kangaroo is using its forearm as a radiator to help cool its body down. It also will seek shade, dig patches away in the soil to find cool places to lay down to keep cool. But evaporative cooling is one of the ways an animal can cool its body down. Plants also evaporate a lot of water. And remember, whenever you evaporate something, you're pulling heat out of something that the water might be exposed to. So if it's a leaf, okay, all these leaves up here in the canopy of the tree are evaporating water. Okay, that's causing the air up between the leaves to cool down. Cold air is heavier than warm air. So if you stand underneath a tree on a sunny day, not only are you in the shade, but you're going to be being bathed in very, very cool air that's going to be falling down around you. So trees are actually acting as natural air conditioners by using the evaporative cooling effect of water. Because remember, water has to absorb or can absorb a massive amount of heat before it changes phase and becomes a gas. Finally, we get to the fact that ice floats. Ice doesn't sink. Now, most substances, when they turn from a liquid to a solid, the solid is denser than the liquid, and things that are denser sink. So, for example, if you take solid wax and you put a piece of solid wax into a dish of melted wax, the solid wax will sink to the bottom. This is what makes lava lamps work. On the other hand, water is just the opposite. Liquid water is denser than frozen water, or what we call ice. So if you look at an ice and a diagram of water molecules forming ice, they form crystals that have spaces. And these spaces actually cause the ice to puff up a little bit, reducing its density, causing the ice to float on the surface of cold water. You don't see the spaces over here in the liquid water. So this has a huge effect in ecosystems because it makes ice float, or makes bodies of water freeze from the top downward, not from the bottom upward. So if you look at a pond, the surface of the pond may be completely frozen. The air above here may be very cold air, maybe extremely cold. And the water underneath may actually be able to be warmer because the ice is forming a barrier between the cold air and the water. So the water is losing heat more slowly because of the insulating effect of the ice. So animals and plants that live in the liquid water don't freeze solid. This is very, very important. Life on Earth would be completely different if ice actually sank. All right, that ends our our video cast here on the properties of water related to hydrogen bonding.